compound angles. Now, to do this, I'm going to do something else first so we can go and create the compound angle formulas. So I'm just putting in the unit circle there. There's the point P. Now, I want to find the coordinates of point P, but I'll do it with reference to that angle there, beta. Using a bit of trig, it's easily shown that x coordinate would be the cosine of whatever beta is, and the y coordinate would be the sine of whatever beta is. So in other words, the coordinates of P is cos beta, sine beta. Now it does not matter where I put the point on the circle, it will always have cos of the angle that it makes with the x-axis, sine of the angle that it makes with the x-axis. So I could put another one over there. Let's call it Q, and we'll say that angle is alpha. It's an obtuse angle, but that doesn't matter. Its coordinates would be cos alpha, sine alpha. But because alpha is obtuse, that would give me a negative x coordinate, so everything's fine. Well, I'm interested in the distance between those 2 points, and there's a couple of ways I could find it. I could use trig and our cosine rule. So pq squared equals 1 squared plus 1 squared minus 2 times 1 times 1, the cos of whatever the difference is between alpha and beta. So I end up with this expression, pq squared is 2 minus 2 cos alpha minus beta. Or I could use our coordinate geometry formulas and just use the distance formula. So pq squared would be the difference in the x values squared plus the difference in the y values squared. And if I expand that out, I get this beautiful expression, but we can use trig identities to simplify this a bit, because you'll notice we have a cos squared alpha and a sine squared alpha. Well, that's going to be 1. We've got a cos squared beta and a sine squared beta. That's going to be 1. So all up, we have 2, but we also have this minus 2 cos alpha cos beta minus 2 sine alpha sine beta. So when I said to you I'm interested in the distance PQ, I kind of lied. What I'm really interested in is PQ squared. I've come up with 2 different expressions that PQ squared are equal to. So logically they must be the same thing. So I now know that 2 minus 2 cos alpha minus beta is 2 minus 2 cos alpha cos beta minus 2 sine alpha sine beta, or tidying that up, we get the first of our compound angle formulas. Cos alpha minus beta equals cos alpha cos beta plus sine alpha sine beta. What happens if I replace beta with negative beta? It becomes cos alpha plus beta. That's cos alpha cos negative beta plus sine alpha sine negative beta. But now we can play around with odd and even functions to tidy this up a bit more. Because remember, cos minus beta is cos beta, and sine minus beta is minus sine beta. Even function, odd function. So putting that in, we get the second of our formulas for cos alpha plus beta. You'll notice they're very similar formulas. The difference is the sign in between them, but you'll notice the sign in between them is different to the sign on the left-hand side. So a much easier way of remembering these. There's the formula. I've written it all as 1. So when it's plus minus, but then on the other side minus plus to highlight the sign change. But this is how we remember it. Cos, cos, sine, sine. That is the pattern. Cos, cos, sine, sine. But if it's not the sine, well, it's not the sine ratio, it's the cosine ratio. No, it's not the sine. Then it's not the sine. And that's how you remember it. Cos, cos, sine, sine. If it's not the sine, it's not the sine. Okay. Now, we'll replace alpha with 90 minus alpha in that original expression that we found. And we'll get 90 minus alpha minus beta, cos 90 minus alpha cos beta, sine 90 minus alpha sine beta. But now I'm going to use complementary ratio ideas. So the cos of 90 minus alpha minus beta would be the same as sine of alpha plus beta. And cos of 90 minus alpha would be the same as sine alpha. And the sine of 90 minus alpha would be cos alpha. So we get sine alpha plus beta is sine alpha cos beta plus cos alpha sine beta. I'm now going to replace beta with minus beta in that one. And again, I will use odd and even functions to tidy up and get this formula. Now have a look. They're very similar formulas. But this time, the sign on the right-hand side is the same as the sine on the left-hand side. So how do we remember this one? Sine, cos, cosine. Sine, cos, cos, sine. But if it's the sine, yes, we got the sine ratio. Then it is the sine. So there's our formula. Sine, cos, cosine. If it's the sine, the sine. What we have to remember when we do this is two things. You start with what you start with. So it's the sine ratio I'm finding, so I start with sine. Whereas with the other one, it was the cos ratio that I'm finding, so I start with cos. And whenever you say cos again. So you always go cos, cos. So the first one was cos, so I start with cos. Cos, whenever I say cos, so I go cos, cos. That only leaves me with sine, sine. Cos, cos, sine, sine. Not the sine, it's not the sine. With sine, I start with what I start with. So I start with sine. So I go sine. Oh, well now I'll go cos. But whenever I go cos, I go cos. So sine, cos, cos, leaves me one to go, sine. Sine, cos, cosine. If it's the sine, it's the sine. Tan, what happens with tan? Well, tan we know is sine on cos. So on the top, sine. Sine, cos, cosine. If it's the sine, it's the sine. On the bottom, we've got cos. Cos, cos, sine, sine. Not the sine, it's not the sine. Let's tidy this up by making it look even more complicated. We'll divide everything by cos, cos. So it makes it look far more complicated, but there is a lot of cancelling that will happen, you will notice. So cos beta and cos beta in the first one on the top, cos alpha and cos alpha in the second one, and then down the bottom a lot of cancelling, leaving with a whole heap of sine on coses, but sine on cos is tan, and we get tan alpha plus beta is tan alpha plus tan beta on 1 minus tan alpha tan beta. Let's replace it with minus beta and see what happens. Now, tan, odd function. So therefore, we get tan of alpha minus beta is tan alpha minus tan beta on 1 plus tan alpha tan beta. Again, comparing the signs, notice on the top of the fraction, it's the same, but then on the bottom of the fraction, it's the other sign. So how do we remember this one? It's easy. It's tan plus tan on 1 minus tan tan. So tan plus tan on 1 minus tan tan. So for that one, I just only ever do the plus one, because then I know if it's minus, I just swap the signs around. So it's tan plus tan on 1 minus tan tan. So these are the compound angular formula. Let's write them all down in their glory. We have sine, sine, cos, cosine. If it's the sine, it's the sine. We have cosine, cos, cos, sine, sine. If it's not the sine, it's not the sine. And we have tan, tan plus tan on 1 minus tan tan. That allows us to expand out our trig, because something like sine alpha plus beta is not as simple as expanding out like normal parentheses and saying, that's sine alpha plus sine beta. Doesn't work. Let us do some examples. We are going to expand this wonderful expression here. Cosine. Cos, cos, sine, sine. If it's not the sine, it's not the sine. You see, you write it as you say it, and then you're just writing it down, what you're saying. Cos, cos, sine, sine, and then you go back and put the sine in. Don't have to remember a formula. Simplify this expression, but I notice the pattern. Look at it. It goes tan plus tan on 1 minus tan tan. Therefore, I know that will be the tan of 20 plus 10. Tan of 30, one of our exact values, 1 on root 3. Find the exact value of sine 15 degrees. What I need to do is create 15 out of the exact ratios, the ones I know. So I know 0, obviously. I know 30, I know 45, I know 60, I go 90. There's lots of different combinations I could have here to get 15. Which way did I go? I went 45 minus 30. Now, but you could have gone 60 minus 45. I mean, there's all sorts of ways you could do it. So it's sine. Sine, cos, cos, sine. If it's the sine, it's the sine. Now I sub in the exact values that I know. It's just a little bit of manipulation. Looks like, we got a common denominator. That's nice. So it's root 3 minus 1 over 2 root 2. No, I don't bother rationalising the denominator. Okay. If sine alpha is 2/3 and cos beta is 1/4, find the sine of alpha plus beta. I don't need to find the angles to do this now, because I can just draw up a triangle for each of those ratios. So there's the alpha triangle. other side would be root 5. There's the beta triangle, other side will be root 15. And then I know sine is sine, cos, cos, sine. If it's a sine, it's a sine. I just read off the triangles, sub in, and there's our answer. 2 plus 5 root 3 on 12. The tan of the inverse sine of 2/3 plus the inverse cos of a quarter. Remember those inverse trig? They're basically just angles. So in other words, I could say alpha, there's the angle, is the inverse sine of 2/3. And I could draw a triangle up for that. And there we go. The third side would be root 5. I'm going to say beta is the inverse cos of a quarter. Again, let's draw a triangle up for that one. And the third side, root 15. Don't make the mistake of thinking these are in the same triangle. Sometimes they might be, but in this case, they're clearly not. All right, we're doing tan, which is tan plus tan, or 1 minus tan tan. Read off the triangles. Ooh, boy, that's a bit more involved. What about if we multiply everything by root 5 so I don't have fraction on a fraction? Oh, well, there we go. Eventually we got it. 2 plus 5 root 3 on 5 minus 2 root 15. And again, no, I'm not going to bother rationalising the denominator on that. 17D, our compound angles. When you go home tonight and your parents say, "What did you learn at school today?" haven't you got wonderful things you can tell them?